Hello everyone, I'm Ziyi. I'm currently a PhD student at EPFL working with Alessandro Chiazza. Today I'm going to talk about our recent work on security for proof-carrying data from Straightline extraction. And this is joint work with Ale, Shaha, and Elon. So before I get started on all the technical stuff, I want to give a very brief roadmap on what I'm going to talk about today. So the first thing I'm going to do is to introduce proof-carrying data. And the short answer of what is proof-carrying data is that it's just recursive composition of snarks. And it's very useful for efficiently verifying distributed computations. But in practice, there is a little issue, namely that PCD is actually deployed under the assumption that no matter how many recursions you do, the resulting PCT is as secure as the underlying snark. But all prior security analysis, they cannot show that. They actually show that there is a huge gap between the security of PCD and the security of one underlying snark. So in this paper, what we do is that we propose a new idealized PCD that model closely the hash-based PCD in practice. And we actually show that for this particular idealized PCD, it is as secure as the underlying snarks, regardless of the recursion depth. So this provides the first justification of the common practice that people use in deployment. So let me start with defining proof-carrying data, PCD. As I mentioned before, PCD is very useful to enable mutually distrustful parties to perform efficiently verifiable distributed computations. So let's look at a very simple example. So now let's say that I want to sum 6 numbers, and I have 6 numbers, and I have 6 distributed parties. They're pandas, not very smart. Their job, each of them, is to sum one number and give me a proof that their computation is correct. And then what I do is just I aggregate their results and also their proof together to reach a final result. So PCD provides kind of an abstract way to model this type of distributed computations in the form of a transcript. And here I just give an example of a PCD transcript with size 8 and depth 3. And what is this transcript doing? This transcript is saying that for each node, which represents one step of the computation in a way, we say that the node is correct if for the given compliance predicate phi, given the current data z, current witness for the computation w, and incoming data and proof, the compliance predicate accept. So if that's true, we say that this node of computation is correct. And we say that, so what is the purpose of this proof here? In the previous example, it does nothing. It's just summing one number, two number. It's a P computation. It's easy to verify. But in general, for harder computations, you actually need proofs. And this proof pi, it not only attests that the current node, the blue one, is correct, but also it says that every child vertex, every child computation here also has a valid proof. So this is a proof of proof. And then the corresponding PCD prover and verifier has the interface where the prover gets all the necessary information for the current step of the computation, the data and the witness and the previous node, provide a proof for the current node, which is proof of correctness and proof of proof. And then the verifier decides whether to accept or reject. And as any other cryptographic primitives, we have security guarantee for PCD. And in particular, what we care most about is this notion called knowledge soundness. And it's saying that for every bounded adversary, P, there exists an efficient extractor, such that this event happened with very small probability bounded by kappa. Namely, the prover outputs a predicate, outputs result, output proof, sent to the verifier, and verifier accepts. And in this case, the probability that the extractor cannot extract a valid transcript that is compliant with the predicate provided by the prover, this event is extremely small, bounded by kappa. So that's the security guarantee we care most about for PCD, and that's PCD. And as hinted at the very beginning of the talk, PCD is actually just can be constructed from snarks. And specifically, we can focus on snark for one particular relation, circuit set, which is saying that it contains the set of tuples of a circuit and assignment where the circuit accepts the assignment. So that's the relation that we care about for snark. And then snark prover and verifier just work as usual. The prover gets both the instance C and the witness A. The verifier gets only the instance. The prover gives a very short proof, and the verifier decides whether to accept or not. And similar to PCD, we also care about non-soundness for snark, which is saying something very similar. It's saying that for every bounded adversary, there exists an efficient extractor, such that if the prover convinces the verifier, then the probability that extractor cannot extract a valid assignment is extremely small, which is bounded by kappa arg, the knowledge-soundness error of the argument, or the snark. Okay, so we mentioned that PCD can be constructed from snark. How do I do that? The very naive construction that actually work to some extent is just to concatenate snark proofs. Now we go back to this very early picture we saw, a PCD transcript. Now we want to use snark to allow the prover to slowly construct up the PCD transcript. So how does it do it? The PCD prover is gonna run the snark prover for the predicate phi. And in particular, it view the predicate phi as a circuit. So the snark works for circuit set, which can testify whether the predicate is satisfiable or not. And then the PCD prover gives all the necessary information to the snark prover, and snark prover output a pi. And then at the end, the PCD prover just concatenates all the proof strings, that the input proof strings, pi1, pi2 it receives, and also the new proof string it received from the argument prover, and concatenate them together. The advantage of this construction is that this is what we hope to be true. The resulting PCD is actually as secure as the underlying snark. But the disadvantage is that this proof string grows linearly with the number of nodes you have in the transcript. So this is absolutely not succinct. You cannot achieve efficient verification. So the working proposal that people actually use is called the recursive composition of snark proofs. And in particular, the PCD prover and verifier just invoke the snark prover and verifier for circuit set for a particular recursive circuit C that I'm gonna define now. So the recursive circuit C, again, receive input, the current computation, and all the child computations. And it check two things. First thing, it check whether the current computation is correct by running it through the predicate that we wanted to satisfy. And it also check if there exist valid proofs for previous computations. So it runs it through the argument verifier, which kind of guarantees you that you have valid proofs for previous nodes. And then the circuit just returns yes, accept, if both check pass. And if the circuit returns yes, you are kind of guaranteed that both the current node and the child computations are correct. And then the PCD prover and verifier, it just run the snark prover and verifier for this particular recursive circuit. And the prover gives the proof, the verifier decides whether to accept or reject. So this is recursive composition, and unfortunately, prior works cannot get very good security for this construction, and in particular, the best analysis at the moment shows that the PCD knowledge soundness error is upper bounded by something exponential in the depths of the recursion, which means that you don't have any security guarantee when the depth of the recursion is bigger than a constant. So it actually still remains a very interesting open problem to find a battery analysis for this case. But today, we're going to focus on a slightly different PCD, a PCD that has a stronger notion of extraction that I'm going to explain in a minute. So what we show is that we actually prove a significantly improved bond for PCD with straight-line extraction, this stronger notion of extraction, or this stronger notion of notch-soundness. And we say that if we start with a snark with straight-line extraction, then we end up with a PCD whose notch-soundness arrow is upper bounded by the notch-soundness arrow. So this is exactly what we want. This shows a significant improvement. In general, this kappa in our construction does not grow with the depth of the recursion, nor with the size of the recursion. But the bad news is that in practice, snarks actually have non-black box notch-soundness, and straight-line extraction that I'm going to define in a minute only exists in idealized models. So how do we apply this theorem in practice? Why do we have this result? Why does it matter? So the main application of our result is actually we propose a new idealization for hash-based PCD deployed in practice is a PCD or quote PCD in the random oracle model. And then we can apply our theorem because this particular idealization is achieved by snarks with straight-line extraction. And this provides the first justification for the popular practice that people use for hash-based snarks, hash-based PCD, sorry. And we also have more theoretical application. In particular, a few years ago, people already started to look at snarks with straight-line extraction in other oracle models. And in particular, CT10 looks at the signed random oracle model, which combine a random oracle model with a signature scheme. And in their paper, they show that the notch-soundness arrow of the PCD in SROM grows linearly with the size n of the PCD computation. But if they use our analysis, they're able to remove this n dependency, multiplicative dependency on the arrow bunch. And similar thing holds for the snarks in arithmetized random oracle model, which came up 2 years ago. Okay, now the last missing piece is to define straight-line extraction. What is this stronger notion of notch-soundness that we use in this paper? So let's start with something simpler. Let's first look at snarks with straight-line extraction, which is the thing that we use to build our PCD by recursive composition. And there are usually snarks in oracle models. For example, in the random oracle model, our favorite idealized model, we still have a prover and a verifier. And again, let's focus on circuit set. So prover takes in the circuit and the witness. Verifier takes in the circuit. But both of them have also oracle access to the oracle function, the random oracle function f. So it's like an oracle gauge that they have. And then, as before, the prover just use this input and its oracle access to the oracle and provide a very short proof to the verifier, and then the verifier decide whether to accept or reject. And we say that the snark has straight line notch-soundness if there exists a deterministic extractor E, such that for all bounded adversary, this event is, the probability that this event happening is very small. So the prover convinces the verifier, and then the prover sent the circuit, the instance, the proof, and a transcript, a trace, a query answer trace, which contains all the queries the prover made to the random oracle function f to the extractor. And then the extractor, the extractor's goal is to extract a valid witness. And straight-line notch-soundness is saying that the probability that the extractor cannot extract in the event that the verifier accepts is very, very small, bounded by kappa arg. And we say that this is straight line because this extractor contrary to the previous one we saw, it does not depend on the prover. It only depends on the correct answer trace. And the wonderful thing is that in oracle models, especially in the random oracle model, this is achievable by our favorite snark, the Mikali snark, the one that is based on PCP or IOPs. So let's see with this snark whether we can use the previous recursive composition to construct PCD. The spoiler is that we actually can, but there's some modification that we need to do. So this is the previous recursion, the recursive circuit, and this is how the PCD prover and verifier functions. But there is an issue. The circuit C now, because of the verifier, the snark verifier now has oracle access to the random oracle. So this red F here. So now the circuit C become an oracle circuit. So let's recall that previously the C-set relation we are considering has circuit C, and if it just evaluates C of A. But this doesn't allow oracle access to F. So we have to consider a slightly modified relation where the circuit C is allowed to have oracle access to F, the random oracle. These two relations are actually different because the first one doesn't depend on the oracle, but the second one depends on the random oracle function that you have. And therefore, the snark prover and verifier we use have to be able to support C-set relation that depends on the oracle. And the way to solve this issue is to use notion called relativized snarks, which was briefly mentioned yesterday night. So what is relativized snarks in an oracle model? Again, we use a very concrete relation, C-set with oracle gauge, where the circuit is allowed to have oracle access to F, the one we saw in the previous slide. And then we just do recursive proof composition. Now everything works. There is no violation in the interface or whatsoever. And then with this recursive proof composition, we're able to achieve PCD also with straight line extraction, which is saying that, again, there exists a universal extractor such that for all adversary bondage, if the adversary makes the verifier accept, then the extractor, given, again, the correct answer trace of the malicious prover, it's with very high probability, it's able to extract a transcript that is compliant with the predicate. So for the last few minutes, I want to briefly mention our main application, how to use our results to set security parameter for hash-based PCD in practice. So a brief warm-up is something I think a lot of you are already familiar with, how to analyze and set parameter for hash-based snarks in practice. So there is a very well-established three-step recipe, where the first step is you first give an idealization of the hash function that you use in the snark, because it's hash-based, which is a random function. And in particular, for any hash-based snark, where we can idealize it as a snark in the random oracle model, if you use the random oracle to idealize the hash function. And the second step is to establish a concrete security bound for the snark in the random oracle model, which you can do, and there are analyses out there. And then the last step is to go back to the hash-based snark and set parameter according to the concrete security for the random oracle snark. So we have to be careful at the first step here in the idealization. This only works if the snark only have black box usage of the hash function. But we're very lucky because almost all snarks that we care about, especially the one based on probabilistic proofs, they satisfy this constraint. So let's see if we can just use the previous well-established recipe to model hash-based PCD. And in particular, we know that in the standard model, a hash-based PCD is obtained by recursive proof composition from hash-based snark. So what if we just idealize the snark, as always, because we like the snarks we have in practice, they have Straightline. They don't have non-black box usage of the hash function. But this is problematic because, as I mentioned very early, the security analysis, the existing security analysis is actually very expensive in the sense that it grows, the error bound for the PCD grows exponentially with the depth of the computation. So we cannot use this. But in general, practitioners still use hash-based snark in practice as if it's as secure as its underlying snarks without justification. Then the natural question to ask is whether we can use our results. In particular, we have relativized snark here, we have PCD here. Can we do a mapping like that? Can we do idealization like that? So the second attempt is actually to follow the arrow, the blue arrow in the previous slide. So what we want to do is that take a hash-based PCD, idealize it to a PCD in a random oracle model, and then do recursive composition from relativized snarks from in the random oracle model. And then apply our theorem, which shows that the arrow doesn't grow. But the first issue is that this idealization actually doesn't work because most PCD, hash-based PCD, have non-black box use of the hash function because of the recursion. And also, what's more troublesome that we don't know how to get around with is that there are impossibility results that I'm actually going to talk about in 3 hours. Recently we showed that relativized snarks actually do not exist in the random oracle model, and this is a very strong impossibility result. It's almost tight with the current non-existing constructions. And also there are very strong evidence showing that, and it's a popular belief that PCD actually do not exist in the random oracle model. And there are partial results proven by the very early paper, the Valiant paper, and Eurocre paper 2 years ago, and also my 2 recent impossibility results. So we cannot apply our theorem directly. So what can we do in this case? We have 2 issues, right? First, hash-based PCD uses hash function in a non-black box way. Second, this impossibility result in the relativized world. But one observation we can make is PCD, by recursive proof composition, actually only looks at the hash function to check correctness. It doesn't destroy the hash function in any way. And moreover, this relativization shows up only because the circuit C, the recursive circuit, is a oracle circuit. It needs to query the random oracle, but it needs to query the random oracle precisely because the snark verifier needs to query the random oracle. So that's the only reason why C is an oracle circuit. So the solution we propose is actually we can forward all the oracle queries that will be queried by C to the prover by asking the prover to attach all the queries C is going to make to the proof string. So then in the recursion, the circuit doesn't have to make oracle queries itself anymore. It only needs to check at the end of the recursion that all the forwarding queries by the provers are correct. So, but the caveat here is that forwarding the queries makes the prover non-succinct, but as an idealization, this is not, especially for security, this is not really an issue. So then we can apply our theorem, take an hash-based PCD, idealize it to a non-succinct PCD in the random oracle model with straightline extraction, which we can obtain from non-succinct relativized argument in the realm with straightline extraction. This actually gets around with the impossibility results that I'm going to talk about in 3 hours because of the non-succinctness. And then now we're happy, we can apply our theorem, and this provides the justification for the popular deployment in practice on hash-based snarks. And that's all. Thank you.
Any questions?
We've heard a lot about like Fiat-Shamir, idealized model, and all these kind of things yesterday. Are you like scared that this particular setting might give us problems in that regards?
Not in particular. Thank you for the question. It's a great question, but not in particular because the whole like all the results we have in this paper and also even in standard model, the PCD security can be guaranteed once you have security for the underlying snark. And in particular, if you are able to, so in other words, if you are able to give me a secure snark whose security is guaranteed by whatever variant of the hash mirror that you can come up with, then the PCD is guaranteed to be secure.
Yeah. Okay, let's thank Ziyi again.
Yeah. Yeah. What? Okay. I have 31 minutes. What?
We're going to start in 1 minute, okay? We're just going to sync with the other room.